This is a case of laminar pipe flow with 1 meter diameter and 3 meter length, and the velocity, entrance velocity is 1 meter per second. So we drag the fluent window into the workbench and name it as laminar pipe flow. Then since our case is axisymmetric, we need to change the properties and change the analysis type from 3D to 2D. And now we can open the new space claim geometry. Now we can go into the new sketch plane, but before that we need to change the units from millimeters to meters. So we can do that by going to File and then Space Claim Options and changing the units from millimeters to meters. Now we will select the XY plane and go to the plan view. Simply select the rectangle and just drag it. The length given is 3 meters, so we'll enter that. And for the diameter, we can simply give the dimension, or rather radius, we can simply give the dimension as 0.5 meter. And we will just zoom out and we can see the rectangle of our case's geometry is ready, and we'll have to return to the 3D mode. And so finally our geometry will change color to green. So now this is the correct geometry, and now we can go ahead and close the space claim. So now we will start the meshing part. Once the meshing opens, what we need to do is we need to generate a default mesh. So we go to mesh, and then we just click generate, which will create a default mesh. Now we need to apply edge sizing, wherein we need to give 100 cells in 1 meter. So we'll do that with the help of the sizing option. We select the left and right boundaries by doing click and control plus click, and then we go to geometry apply, and it will show 2 edges. And what we need to do is change from element size to number of divisions, and since the length is 0.5 meter, we need 50 divisions. And we change the behavior from soft to hard. Now we again apply the sizing on the top and bottom edges. Similarly, by doing click and control click and applying the geometry. We need to check the 2 edges option is on. Again, number of divisions, and this time it will be 300 divisions since the length is 300 meters, and changing the behavior from soft to hard. And we also need to do the face meshing, so we select the whole face, click anywhere in the face, apply, and we need to make sure that quadrilaterals is selected, so it will give us a quad mesh. Once these 3 options are selected, we can go to mesh and then right click and update, and it will create the mesh. So here we can see it's all the elements are square, so we know that our mesh is correct. And now what we need to do is we need to name our boundaries. So we'll choose the edge selection filter, go to the left boundary, right click and select the create named selection option, and we choose inlet. Similarly, we'll do it with the top boundary as well. Right click, name selection, and then we can name it as wall. and similarly we'll do for the right and bottom boundaries as well. So here's the outlet, and there is the axis. So now that the mesh has been created, we'll just check whether all the name selections have been done, and then we can just go on and close the meshing. Then we'll just right click and update the mesh, and once the tick comes on, we can go on to setup, which basically opens ANSYS FLUENT. And then the Fluent dialog box will open, and we can just go ahead with the default values and start. So yeah, once Fluent is loaded, what we need to do is our simulation needs to be steady state simulation, and in the 2D space it's not actually planar, but we need it to be axisymmetric. In models, we don't need to change a lot. We just need to change our viscous model to Laminar, since our Reynolds number is actually quite low. And then we need to add a new material, so we can just right click on fluid and choose new, and we can name the material anything we want. We are more concerned with the properties, so we will change the density as well as viscosity. So the density is 1 and viscosity should be 0.1, so we will change that. And then change create and then close. Then we can check whether the material has been created or not by just double clicking on the materials, and we can see it has been. And now we will assign the material, so we need to go to the fluid and then click the surface and then change the material from air to fluid 1, so that the correct properties get applied. Apply the boundary conditions, and so starting with axis, we'll go with axis as well. And inlet, it will be velocity inlet. We need to specify the velocity, so we edit, and we need to specify the magnitude normal to the boundary, that is in x direction, and the magnitude given here is 1 meter per second. So we'll just apply and close, and then for interior we'll keep it as interior only. And outlet, we need to change the boundary condition to outflow, and then apply and close. And for the wall, we need to check whether it's no slip or not, and yeah, we can see that the no slip condition has been applied. So now that we have applied the boundary conditions, what we need to do is go to the solution methods, and so we will be using the simple scheme for the pressure velocity coupling solution. Similarly, for gradient, the least square cell base, pressure, second order, and first order upwind for momentum. And now we don't need to change the controls. We'll just go straight to the residuals. So the default residuals, as you can see, are set as 0.001, 10 power minus 3, but we need to change it to 10 power minus 6 to get a better, more accurate solution. And just click OK. And then we'll initialize the solution, standard solution, keeping the default values, and we'll just initialize it, and then go to a run calculation, and we need to specify the number of iterations, so we can go for 2000 iterations, and then we'll go to calculate. And once the calculation happens, and once the calculation is done, we can see the residual plot, and we can see that the final residuals are quite low, so we can go on and close Fluent. and then we'll open the results tab, so which opens the post-processing software of ANSYS, that is CFD Post. And so here we can see our axisymmetric case for a very small angle, and we can see that periodic one and periodic shadow are the two faces of the pipe. And now what we need to do is we need to plot first the velocity contours. So we go to contour, and we can just name it as velocity contours, and then okay. Now the location will be periodic 1, and what we need to do is plot the variable velocity, and we'll change the number of contours to 101 just so that the contours will be smooth. And we just check, yeah, so we will, for draw mode, we'll set as draw as points and disable the show contour lines options, and then just click apply. And here we can see the velocity contours, and the maximum velocity is around 1.92, a bit more probably. And we'll also do the exact solution as well and create the parabolic velocity profile. But first we'll create the pressure contours in a similar manner, and just same steps as before. The location periodic 1, and the global variable is pressure. Changing the number of contours to 101, and changing it to draw at points, and disable contour lines, and apply. Then just disable the velocity contours. Yeah, so here we can see the pressure at every point in the pipe. So now that we have plotted the contours, what we need to do is we need to check the exact solution. So what we'll do is first we'll check the velocity profile. So we'll create a line at x equal to 2.5, a vertical line at x equal to 2.5, and we'll just name it as velocity profile line. And just mention the endpoint, so 2.500 and 2.50, since 0.5 is the radius. And we'll take 100 sample points to get a smoother graph, and the rest we'll just leave unchanged and then apply. And we can see here the line has been drawn. Yeah, now we'll go to chart and just name it as the velocity profile, and so it will be an XY line chart, and we'll change the title as well to velocity profile. Yeah, velocity profile at x equal to 2.5 meters, since the flow is fully developed at that stage. And so location will give us the velocity profile line, the one we just created, and on x-axis we want the velocity, and similarly on the y-axis we'll plot the y distance, which is basically the radial distance, and the rest will remain unchanged, and then apply. And so here we can see the parabolic curve, and we can see the maximum velocity is approximately 2, which is good because the u max should be 2 into u average, so it should be 2 into 1. And we'll just change the series name to velocity, and we can also see the no slip condition being applied, since at y equal to 0.5 the velocity is 0. Now we need to plot the center line pressure, so we'll plot another line. Just first we define the line, just name it as center line. Now we'll again just mention the endpoints, so 0, 0, 0 and 2.5, 3, 0, 0, and again number of sample points 100, and keep the rest as default and apply. And we can see the center line has been created as well. And yeah, and once again we will go to the chart option and name it as centerline pressure. And we'll change the title of the graph as well. And this time our location will be the center line, and we'll change the series name to just pressure. And on the x-axis we need to plot the x variable, and on y-axis will be pressure, and keep the rest as default and apply. And yeah, we can see the variation of pressure along the center line. As the flow develops, the center line pressure will tend to decrease. Now what we can do is we can plot the wall shear stress as well. So we need to define a line for the wall. So before that we'll just change the view a bit so we can see the line properly. Just pan it a bit, and then we'll again just define the line. Just name it as WSS line, so wall shear stress line, and the line will be 0.50 to 0.50, and just change the number of points, sample points to 100, and keep the rest as default and apply. And we can see the line for the wall has been created as well. So again we'll go to the chart option and just name it as wall shear stress. And we'll change the title as well to wall shear stress versus length. And change the location will be the WSS line, and we'll change the series name to wall shear stress. And so on x-axis we'll keep the x coordinate, and on the y-axis we'll keep the wall shear. And the rest is default and apply. So yeah, here we can see the variation of wall shear stress. As the flow becomes developed, the wall shear stress becomes constant. And yeah, so in this way we have completed the post-processing. And yeah, so we can see the different charts. For example, the velocity profile, the center line pressure, wall shear stress versus x. And similarly, we have also done we also plotted the pressure contour as well as the velocity contours. And so that's it. So we can now just close CFD post, and that's the end of this exercise.